Welcome to section 2.9 of our linear algebra notes, dimension and rank. Today we'll talk about coordinate systems, how to compute coordinate vectors, and we'll also learn about the dimension of a subspace and how to compute the rank of a matrix. So let's say you have a set of vectors that form a basis for a subspace H. Then for each vector in your subspace, it has coordinates related to relative to the basis. So this is essentially if you write your vector as a linear combination of your basis elements, then you take the coefficients and you put them in a vector themselves. Now, one important thing I want you to make note of, and we'll see an example of this soon. So H is a subspace of some Rn or Rm, some vector, vector space there. And so when we have a basis, so H might be sort of smaller, it might have less vectors. So P could be less than, the number of vectors in the basis could be less than n. And so this coordinate vector might not be in Rn, it's in Rp. So just hold on to that and we'll talk about that a little bit more. So this is called the coordinate vector of x relative to the basis b, or sometimes the b coordinate vector of x. So let's consider a subspace H given by two, and this is a subspace of R3, and it's given by basis vectors B1 and B2, which are really E1, if you remember our notation from before, this is E1 and E2. So if we think about what H looks like, well, remember a basis spans a space and is linearly independent. So when we look at the span of these two vectors, what we get is everything that looks like something times that first vector plus something times that second vector, and where that something is a real number. Well, that's another way to write that, is that we put that together, we multiply it out, and we get just vectors where we have the first two entries are real numbers, and then the third entry is a 0. And so we've already seen kind of why, so to understand why these form a basis, well, first of all, and I guess I should keep calling them B's since that's what I called them up above. So first of all, they do span our space by, so let me write this down. Oops. So the B1, B2 span H kind of by definition. And then if you look closely at them, they're linearly independent since there's a pivot in every column of the matrix that you get when you stick those vectors into a matrix. So they're span and they're linearly independent, so they form a basis. Now let's write down the b coordinate vector. So here, this x, if we write it in terms of these basis vectors, we have 4 times the first one minus 2 times the second one. So that's 4 times b1 minus 2 times b2. So the coordinate vector for x with respect to our basis is going to be, since we have 2 vectors in our basis, it's going to have 2 entries. And so the coordinate vector is in R2, even though that vector x is in R3. So just something to keep in mind. Okay. So now for our quiz, I just want you to put in the top entry in this particular given coordinate vector. Okay, so now let's talk about a notion of dimension. So we have an intuitive understanding of dimension, and our intuition will kind of remain, it's true to us. It's what you think it would be. So the dimension of a subspace is the number of vectors in a basis. And that's why, I guess here is the one place where it's a little weird. That's why up here in our example, in part 1, since we had 2 vectors in a basis for H, the dimension of H equals 2 and not 3. Even though H sits inside R3, its dimension is the number of vectors in a basis. So why does this match up with what you think about dimension? It's the number of degrees of freedom, the number of directions you can move in. Okay, so we always say that the 0 subspace has dimension 0, and let's look at if we have vectors R3. Well, one basis for R3 is the set 1, 0, 0, 0, 1, 0, and 0, 0, 1. It's pretty easy to see that those vectors span R3 and are linearly independent. So the dimension is 3. And your next quiz asks you about the dimension of Rn. Now, thinking about lines, well, we generally think of a line as a one-dimensional thing, so hopefully that will be true here as well. And if you think about a line, even if it's in R4, which I can't draw, but if you have a line, you have one vector, and then you look at its span, and that gives a line. So if this is a vector u, the span of u is a line, and one vector is always linearly independent, so u forms a basis for this line, and so the dimension is just that one vector, which is good because we think of lines as being one-dimensional. This is true in general. A plane in R3 is a two-dimensional subspace of R3, and that's why we talk about it having dimension 2. So that's what's happening up here. We have a space that has, it's going to end up being a plane. It just doesn't go up. This is really the XY plane. In fact, we could even say that. So H is the XY plane. It just doesn't go anywhere in the Z coordinate. And so that's why it has dimension 2, even though it sits in a three-dimensional space. Okay, so now if we want to find the the dimension of the null space of a matrix, well, actually, if you think about it, so that's the set of all solutions. Well, let me write this carefully. So the null space of A is the solutions to AX equals 0. And so typically we write in parametric vector form. And so we're looking at the span of those. And so the number of vectors in that is equal to the number of free variables. And well, you can figure that out by counting pivots and subtracting those pivots, the number of pivots, from the number of columns. So the dimension of the null space of A equals the number of columns in A minus the number of pivots. And another way to think of that is the number of free variables. And this sort of makes sense because a free variable is free. It's a degree of freedom. So the dimension is the number of degrees of freedom you have, the number of directions you can move in. We also have a notion of something called rank. So the rank is actually the dimension of the column space. So we've talked about the dimension of the null space is free variables. And then the column space, well, that means we want to know the number of, let me write this up here, the number of vectors in a basis for the column space of A. But if you remember back to last section, a basis for the column space of A is given by the pivot columns. So that means all we need to do is count the number of pivots. And so in this case, the rank of A equals 3 because we have 3 pivot positions. and I'll let you try the quiz, the rank of this other matrix. Okay, so now we can take this to a more abstract level. Let's say we have a 6x4 matrix. So this is kind of a tall matrix. And its rank equals 3. So that means we have 3 pivot columns. And we want to know the dimension of the null space. Well, we have one more column remaining since we have 4 columns total. So we have 1 free variable. So the dimension of the null space of A in this particular case equals 1. We're going to try to say that in more generality. So now let's say we have a 5x7. So this matrix is a little bit wider. And then we're asking, what's the sum of the rank? Well, that's the number of pivots. And the dimension of the null space is the number of free variables. But every single column is either a pivot or contains a free variable. And so this sum equals the number of columns, which in this case is 7. So in general, and this is called sometimes it's called the rank nullity theorem. So the rank of a matrix A plus the nullity, the dimension of the null space of A, equals the number of columns of that matrix. And why is that? Well, again, the rank is the number of pivots. The nullity is the number of free variables. And so that every column is accounted for now. Okay, so one more question about this. So if we have an m by n matrix, we want to understand what we can say about the sum and dimensions of the column space of A. So let me write this down. So we want the dimension of the column space of A is the rank of A plus the nullity of A transpose. And A is m by n. Well, let's just try to understand a little bit about the rank. So the rank of A equals the number of pivots in A, which we've already seen that the number of pivots in A is equal to the number of pivots in A transpose. So we can write that down. But that's the same thing as the rank of A transpose. And now our theorem, our rank nullity theorem, applies just as well to a transpose matrix, right? So the rank equals the number of columns of A transpose minus the nullity of A transpose. And since A is m by n, its transpose is n by m, so we have m columns. So putting this together then, we have the rank of A. So here we have the rank of A equals m minus nullity of A transpose. So that means the rank of A plus the nullity of A transpose equals m. And so if you compare that to the theorem above, we have, if we want to get m instead of n, we take the nullity of A transpose instead of A. And then finally, we have a little bit more invertible matrix theorem. So if we have an n by n matrix, then each of these statements is equivalent to the statement that A is invertible. So if A is invertible, well, then we know that the columns of A span Rn, And so that's how we get this second thing. And let's see. And that means we have a pivot in every row. And since it's a square matrix, we have pivot in every column. And so now we know the columns are linearly independent. We have that from our old invertible matrix theorem. And so we know that they form a basis because they span and are linearly independent. The dimension is the number of pivots. There's a pivot in every row, so the dimension of the column space is n. And the rank is also the number of pivots. So this both comes from having n pivots. And now the null space, we'll remember that the rank plus the nullity equals n. And so the rank, so n plus the nullity equals n. So the nullity, just the dimension of the null space, equals 0. And so it is just the 0 vector.